Hello everyone, welcome back to Food Science. This is the second video on food science of carbohydrates. Let's talk about the food chemistry of carbohydrates. The first thing is gelling, polysaccharides and their modified forms that can be used for gelling so that it increases the food system's viscosity. It can form gels to stabilize emulsions, suspensions or foams. So let's talk about the gelation of pectin. We learned about pectin when we were learning about the oxidation reactions, where we talked about the formation of uronic acids. So pectin is a polysaccharide which is having D-galacturonic acid, and these are linked by alpha-1,4-glycidic linkages. There are two forms of pectins, as high methoxypectin and low methoxypectin. That depends on the degree of esterification, because these galacturonic acids undergo esterification with methanol or acetic acid. Anyway, there are two forms, two types, as high methoxypectin and low methoxypectin. The top diagram in yellow color is high methoxypectin. This can form hydrogen bonds among the sugar molecules, and it forms a gel like that. So for this gel to form, it is preferable to have a low pH, like a pH less than 3.5. So in the presence of the low pH or the acid, and when we have this sugar, pectin, it can form a gel in the food system. Low methoxypectin, as you can see in the diagram below, it forms gels, but only in the presence of calcium ions. So pectin forms these interactions with the calcium, and it forms a structure like this. So then it forms a gel. Gel means we have this sugar and thickened. It forms water inside. It forms a three-dimensional structure, which is now not really flowing, but it's a three-dimensional structure. So these gels you can see in the jams and jellies, and this low methoxypectin jellies can be seen where we need the presence of calcium ions. For example, if we make a yogurt using fruits and milk, then low methoxypectin will be used to form this gel structure. The next reaction we are talking about is gelatinization of starch. Gelatinization happens when we heat starch in the presence of water. So we need to have three things. We need the starch granule, water, and high heat. When we are heating water, the kinetic energy of the water molecules increase, and this energy breaks down the hydrogen bonds between the starch molecules. And also, starch molecules, while they break their own hydrogen bonds, they form new hydrogen bonds with water molecules. As a result, water comes into the starch granule. When the water is coming into the starch granule swells, and at some point, the starch granule can even burst. As a result, the starch granule loses its crystalline structure. And when the starch granule bursts, some of the amylose chains, they can come out of the starch granules into this surrounding water. As a result of this amylose coming out, the thickness of the surrounding water increases. Thickness or the viscosity. That means it becomes more reluctant to flow. You can see this happening in sauces, gravy. When we add cornstarch to thicken the sauces, this is what happens. And also you can see gelatinization of starch occurring in rice, pasta. When we boil rice in water, the grain becomes more soft. So this is also happening because the grain absorbs water and its texture becomes more soft. What happens in bread? So in bread, we have the starch, we have high temperature, and we have water, but the amount of water is limited for it to undergo a full gelatinization. But to some extent, yes, gelatinization can also happen in bread. So what happens if we start cooling this gelatinized starch? Gelatinized starch, or which is now formed into a viscous paste, if we cool this rapidly with mixing, it forms a more viscous paste. Paste means this can still like flow. But if we rapidly cool it without mixing, this then forms a gel. Gel is like a three-dimensional structure which holds water inside, outside it's thick, so it's not flowing. So this difference comes up with the mixing. If we rapidly cool with mixing, we can form a thick paste. If we rapidly cool without mixing, this forms a gel. And the next reaction is retrogradation. This is also happening in the gelatinized starch. If we cool the gelatinized starch now slowly, then it undergoes retrogradation. This amylose and amylopectin chains, which has previously lost its three-dimensional structure due to heating, due to undergoing gelatinization, now they realign themselves. They try to realign themselves, and this becomes more crystalline. So this solubilized swollen state, which we could see during gelatinization, is now becoming insoluble, shrunken, and crystalline. So this is what you can see when you keep leftover rice for a long time. It becomes hard. Leftover boiled rice. So it becomes harder, it gets a harder texture due to retrogradation. And also this happens in bread because, as I told, bread undergoes some extent of gelatinization. This condition in bread is called stale bread, like it's no longer fresh. Now let's talk about modified starches. Uh, Starch, which is extracted from grains, they are treated in different ways so that they have the ability to keep the texture and the structure of food. These modified starches can be seen in products that need to be microwaved or freeze-dried, cooked at high temperatures. For example, in ready-made pizza, instant soup, sauces. So the first type of modified starch we are going to discuss is the pre-gelatinized starch, which means this starch has undergone gelatinization previously. And it's coming in powdered form because it's gelatinized and then dried. So this powder, if we just put this into water, it forms a thick mixture. We don't have to apply the heat because it has previously already undergone gelatinization. We can see this in instant pudding mixtures. We can just add water and form it into a thick mixture, thick paste without the application of heat. Then we have extruded starches. Extrusion is a process where the material is pushed through this plate. Inside this plate, the material undergoes high temperature, pressure, and mechanical forces. So this breaks the hydrogen bonds and it can transform the structure into a new structure. So this is happening during the production of biscuits, pasta, breakfast cereals. We can add flour into this system and we can get the edible products, which is pasta or the breakfast cereal. The next modified starch is dextrine. To produce dextrins, starch has to be heated to higher temperatures like 100, 200 degrees Celsius with small amount of acidic or basic catalysts, and that causes degradation. As a result, we can obtain white or yellow powders, which are dextrins. These dextrins are used as adhesives or thickeners in foods like candy, confectionery, and also they can be used as fat replacers because dextrins can bind with water and forms a paste. This gives a texture which is similar to what is given by the fat. And then we have thin boiling starches. When this to produce them, the starch undergoes partial acidic hydrolysis, and this product is not very soluble in cold water, but these are readily soluble in boiling water. These thin boiling starches are also used as thickeners. Uh, they are used to achieve a particular texture which is not too thick, but not too thick. Now let's talk about some other applications of carbohydrates in food industry. Carbohydrates can be used for a wide variety of applications like stabilization of emulsion in milk, water binding, stabilization of emulsion in meat, stabilization of ice cream against ice crystal formation, jelly formation for meat, fish, and vegetable products, stabilization of protein form in beer, whipped cream, meringue, chocolate marshmallows, prevention of starch retrogradation in bread and cake for water binding, for thickening. We have already learned about pectin, but there are other polysaccharides giving these benefits: carrageenan, algin, pectin, agar. So we will discuss about some of these carbohydrates in detail. Agar is the first polysaccharide, which is having wide variety of applications in food industry. Um, so you might have heard about agar because very commonly we use agar in the media preparation for microbiology. I've given that within brackets because here we are talking about the food chemistry. So this agar can form a gel which is heat resistant, and these are used in sherbets of frozen desserts, ice cream, to stabilize yogurt, candy, and that can retard the bread staling because that can bind water, and it provides the desired gel texture in poultry, meat, canned products, and in it is used for water binding, stabilization of emulsions in meat products. Then coming to alginates, it's also another polysaccharide which has a wide variety of uses in food industry. That is also acting as a thickener, stabilizer, and gel forming agent. This is used to stabilize the consistency of the filling of baked products, and also in salad dressings, milk chocolates, and it can prevent larger ice crystal formation in ice cream during storage. So what's the disadvantage of these large ice crystals? Ice creams need to have smaller ice crystals, and if they are large, that doesn't give the smooth texture to the ice cream. And these large crystals give some grainy texture, coarse, crunchy, which is not preferable. And these alginates are also used in other applications like forming gel products, pudding, fruit gels, dessert gels, and to stabilize fruit juices and beer foam. Then we're talking about carrageenans. They also have the ability to thicken, increase the viscosity of the solutions, stabilize emulsions, and they are also used in chocolate milk to prevent fat droplet separation, and it stabilizes the suspension of cocoa particles, prevents syneresis of fresh cheese. What is this syneresis? It is the liquid coming out of the cheese. Once we coagulate the milk, it forms a cheese, and this way of the cheese is coming out as a liquid. So that is called syneresis, which is not preferable. So carrageenans can be added to prevent that. And also carrageenans can stabilize ice cream and improve the dough properties and enable higher amount of milk powder incorporation if we use them in baking. And then comes gum arabic, which is also having similar emulsifier stabilizer properties, and it also retards sugar crystallization and fat separation in confectionery, prevent large ice crystal formation in ice cream, and stabilize the foam in beverages. So this is the end of the second video on the food science of carbohydrates. In the next video, let's talk about carbohydrate analysis and let's learn a little bit about the sweetness. Thank you.